I am in the physics department here at UVA. I work for the polarized target group, and our main mission is to understand the nuclear structure of the atom. And in order to do that, we need three key ingredients. First, being a very strong magnetic field. Second, a finely tuned laser. And third, temperatures colder than even the deepest reaches of outer space. My lab focuses on the most challenging aspect of the three, which is the cold temperatures. And to give you an understanding of the scale of how cold this is, over here we have room temperature, which is about 77 degrees Fahrenheit, all the way down to the theoretical coldest temperature, absolute zero. The temperatures that we require are just a hair above absolute zero. And we achieve these temperatures with a device called a dilution refrigerator. A dilution refrigerator takes two different types of helium, helium-3 and helium-4, along with a set of pumps, in order to cool down liquid helium from its boiling point down to the temperatures that we require. It does this in two key stages. The first stage is what we call the evaporation stage. In the evaporation stage, we have a container that we call the bath. We fill it up with liquid helium, and we use some of the pumps to remove the hotter vapor from the cooler liquid. And by doing so, we lower the average temperature down, just a hair. You can think of it as a similar concept to blowing on a hot cup of coffee before you drink it. Once it's cold enough, we send that mixture of helium-3 and helium-4 through the bath to cool down, and it travels down to the target chamber to begin the second stage, the dilution stage. In the dilution stage, the liquid helium-3 and liquid helium-4 separate into two separate phases, and they sit on top of each other, kind of like oil and water. And what happens is the individual helium-3 atoms are so crammed together and cramped, they're desperate to get free and have some breathing. So what they do is that they break through the boundary between the two liquids and enter the helium-4 liquid phase. And by doing so, they lose just a little bit of energy, and that little bit of energy loss corresponds to a lowering of the temperature. This continues until we reach our target temperature of about minus 459.5 degrees Fahrenheit. So when we actually run our experiment, our target material of choice is the deuteron, which is just literally a proton and a neutron stuck together. We load our target material into the dilution refrigerator. We cool it down, we stick it in a high magnetic field and fire the laser at it. What we think will happen when we fire the laser at the deuteron is that at a very specific frequency, the laser will cause the proton and the neutron to fuse into one larger particle. When that larger particle exists for a brief moment in time, and when it disintegrates, it sends a signal to our detectors, which we then record, compile that data, and analyze when they experiment and stuff. Now, it may not have some overarching reaches, kind of like cancer research and stuff like that, but my research does have implications for other fields of physics, namely astrophysics. The first being solving some mysteries regarding neutron stars. Neutron stars are the second densest objects in the universe and are the remnants of former larger stars. And these neutron stars have massive magnetic fields, but we're not exactly sure why. We think that the existence of those merged particles can help explain that and bridge the gap between theory and experiment. The second regards a question that from the very beginning of the universe, the Big Bang. When the Big Bang occurred, it created very simple elements such as hydrogen and helium and just spread across the universe. Now, when we tried to record and figure out what the composition of that early Big Bang molecular soup, we had a theory for how, like, what the ratios of different molecules and isotopes were, but for some reason it doesn't match with what we observe. So those larger merged particles can't help but explain. Thank you for your time.